Hello, and welcome back to another episode of the Curiosity Monkey podcast. Now, if you've lived or been in the UK this winter, you'll have noticed it's been so wet. Now, I live in the southwest of the UK, and although we often get more rain than the rest of the UK here, the past few months have been particularly wet. So, if we look at rainfall data for January, weather station in Camborne, which is in Cornwall, received 240 millimetres of rain in the past January 2026. Now, when we compare this to an average of 120 millimetres between 1991 and 2020 average, we can see that the previous month received double the average rainfall. Now, this is not just limited to the southwest. Other parts of the UK have also seen higher than average rainfalls in the past winter. Now, we've talked a lot about climate change in this podcast, and most people have heard about the typical effects of climate change across the globe. But the climate isn't changing uniformly everywhere. So in this episode, we will explore what the data shows about how the UK's climate has changed to present. We'll quantify just how much specific variables, including average temperature and rainfall, have changed in the last 50 years or so, and we will see if this rate of change is increasing, i.e., is climate change accelerating? Towards the end, we'll briefly cover a little bit on what a future UK climate may look like under different scenarios, as well as some theory on how these models that make these predictions work, and the potential uncertainties with them. Now, this episode mostly covers information from a paper published in 2025 called State of the UK Climate in 2024. And now this work is mostly by the Met Office, and I'll include a link to this paper in the description if you wish to read more on it. It's open source, so everyone should be able to read that, no problem. And as well as this, I'll talk about some of my own findings after doing a little bit of my own data analysis using the data collected and processed by the UK Met Office. Now, this data is open source, and I will link it in the description in case anyone is interested. So before we start examining the data itself, I think it's worth explaining how organisations such as the Met Office are able to interpret climate information in a meaningful way. For instance, suppose we want to know the average temperature in Britain in 2025. We clearly can't measure the temperature at a single point and treat it as the representative of the whole country, as temperature varies quite significantly from region to region. So, quite obviously, the temperature in Edinburgh is going to be different to the temperature in London, which is going to be different to the temperature in Camborne. If we add more weather stations, this can help, but even then, conditions can differ relatively noticeably over short distances. So we need quite a dense network to capture the variability properly. So in practice, this process looks something like, well, firstly, weather stations are distributed across the UK, and they continuously record variables such as temperature, rainfall and wind, and there are around 350 weather stations spread across the UK. The data is then quality controlled to remove suspect values, and the observations can then be interpolated such that each variable can be represented as a function of space and time. Finally, the data can be mapped onto grids at specific resolutions, for example 5 by 5 kilometers, with a single representative value assigned to each grid cell. So basically what this looks like is you split the UK surface area into, say, 5 by 5 kilometer grid cells, and each cell will have one value assigned to it for each variable. So for instance, 1 temperature, 1 maybe pressure, or 1 wind speed or something like that, velocity. And this is the basis of the HAD UK gridded dataset, and this gives conditions daily at variable resolutions. So I'm pretty sure they go all the way down to 1 by 1 kilometre, and you've also got 5 by 5 kilometres, maybe 12 by 12 and 60 by 60, but I can't remember the exact specifics. But yeah, variable resolutions. And datasets like these are really, really useful because it's much easier to see and compare changes in conditions across different areas. Yeah, so these gridded datasets basically give an idea of all of the variables at every point in the UK and with time. So how is the UK climate changing? Well, firstly, we'll look at temperature, because when people think of climate change, this is one of the first things that comes to mind, and particularly the increase in global average surface temperature. That is, it's getting warmer. You know, a lot of the time when people are talking about climate change, they're talking about global warming. But if you listened to this podcast before, you may have heard us talk about how the Earth is not warming uniformly. Some areas are warming noticeably faster than others. For instance, it's well established now that the poles, say the Arctic and Antarctic, are warming at a higher rate than the rest of the planet. This is a phenomenon known as Arctic amplification. Now, if you are interested in Arctic amplification and the reasons for this, then we have a full podcast episode on it. But one of the reasons why the Arctic is warming faster than, say, the tropics is because of this ice feedback. So as the temperature of the Earth increases, the ice melts. Now the ice is relatively reflective for incoming solar radiation, particularly that short-wave light radiation that comes in. So when there's loads of ice, lots of radiation is reflected. But when this ice melts, less radiation is reflected and more is absorbed by that darker coloured ocean, and thus increasing the warming and thus melting more ice, and so the feedback loop is kind of a positive amplifying effect. So how has the UK's average temperature changed, and how does this compare to the global average? Well, the UK's climate has warmed steadily from 1980 onwards. Since the 1980s, the UK has been warming at approximately 0.25 Celsius per decade, but with the 2015 to 2024 decade being about 0.41 degrees above the 1991 to 2020 average, and 1.24 degrees warmer than the 1961 to 1990 average. And the last 4 years have been in the top 5 warmest on record for mean temperature for the UK. Now, 2025 was the hottest year on record for the UK, with an average temperature of 10.09 Celsius. Now, 2024 was also relatively warm, with an annual mean temperature of 9.79 Celsius. Now, the Central England Temperature Series is the longest running instrumental temperature series in the world, and here it starts at about 1660 and runs all the way to present. And the Central England Temperature Series is very clear in showing that recent warmth we've seen over the past decade or so has far exceeded any observed temperatures in the last, over 300 years now. And 2025 was the warmest year in the whole 364-year Central England Temperature Series. So I did a small investigation of my own. I used that HAD UK gridded dataset. I'm pretty sure I used the 5 times 5 kilometre one, and looking at that 2015 to 2024 average of mean temperature and comparing it to the 1991 to 2020 average, it's clear everywhere in the UK has experienced warmth, basically a warming anomaly. It seems that the southeast has warmed more than the rest of the UK. In addition to increases in average temperature, it seems that the frequency and intensity of extreme temperatures in the UK has also risen. The number of days exceeding 28 degrees Celsius is more than double, while days above 30 degrees is more than 3 times that when comparing 2014 to 2023 to the 1961 to 1990 baseline period. Now, temperature anomalies have also become more common. During the most recent decade, so 2015 to 2024, the number of days exceeding the 1961 to 1990 average by 5 degrees is double, and by 8 degrees is treble, and by 10 degrees is 4 times that. As well as this, it seems that temperature extremes are increasing faster than the mean temperatures. So, for example, the hottest summer days are warming at roughly twice the rate of the average summer days. This means that if the UK's average summer temperature rises by 1 degree, the temperature of the hottest days, say the 95th percentile day, increases by 2 degrees. So if we look at 2022, the UK recorded its highest ever maximum temperature of 40.3 degrees Celsius, and within the decade 2015 to 2024, all-time monthly maximum temperature records were set in 5 months of the year. So January 2024, 19.9 Celsius, February 2019, 21.2 Celsius, July 2022, 40.3 Celsius, November 2015, 22.4 Celsius, and December 2019 of 18.7 Celsius. Now I did a little bit of my own analysis. I picked the weather station London St James Park, and that has been recording data for the past, say, 110 years or so, give or take. Now I found that the average temperature has increased over this time period, with 2025 being about 1.5 Celsius above the starting time, say around 1912-ish. The maximum temperature per year has also increased relatively dramatically, as well as the number of days in a year above 25 Celsius. Now if you're interested in looking at these figures, I will post some of them on the Curiosity Monkey Instagram. They're quite interesting just to see how these temperatures are evolving. So what's the cause of all this warming? Well, the most obvious cause is the increase in greenhouse gas emissions that have been observed globally. So anthropogenic emissions have not yet peaked, and so the concentrations of carbon dioxide in the atmosphere are still increasing each year, more than they were the previous year. And there's this acceleration in concentration, so each year we're adding more carbon dioxide than the previous year, and so you get this acceleration in concentration. However, when we look at something such as mean temperature, we see in the past 10 years the UK has warmed up a relatively much higher rate than in the previous decades, more than what can be explained by an increase in emissions. So what would cause this much higher increase in temperature over the past decade or so? So one potential cause of this could be that in the West, our air is quite a lot cleaner, mostly from the reduction of polluting coal burning. So as we phased out coal, we have also reduced the number of sulfate aerosols that have been emitted, that have been dispersed over, say, the UK, but also the rest of Europe. And sulfate aerosols have kind of a double-pronged effect. Firstly, they are pretty reflective, so they reflect incoming solar radiation through the atmosphere back out to space, so it cannot be absorbed by the Earth's surface, and reducing the warming. But B, sulfate aerosols have another effect of, well, water, like vapor in the atmosphere, can condense upon them, so the increased number of aerosols leads to more cloud droplets, and so higher cloud brightness, which reflects more solar radiation. But as we've moved away from coal, it seems that we are unmasking some of this warming that we should have seen in previous years, but we weren't, because we had these sulfate aerosols. So in the past, when there were higher concentrations of sulfate aerosols in the atmosphere, they were reflecting more radiation, and so kind of masking that warming. But now we've reduced our aerosol pollution in terms of sulfate aerosols, we are unmasking or uncovering a lot of this warming, and so we're seeing, potentially due to this cause, a bit of an acceleration in warming in the previous years compared to decades before. We also know that it's not just down to the increase in radiative forcing in the UK atmosphere that affects the temperature in the UK. So what I mean by that is it's not just due to increase in greenhouse gases concentration that basically traps heat in the atmosphere that can affect UK temperatures. We also may experience, say, warming or cooling effects through heat transport from the ocean and the atmosphere. So one large prominent example of this in the UK is that the Gulf Stream transports warm water from the equator, making the UK relatively warmer than it should be without this. So if climate change causes changes in the circulation patterns, either that be in the atmosphere and oceans, this could change heat transport and so the temperatures. But that's unlikely to have a massive impact to date, although there's uncertainty about how this may change in the future. You may hear about people saying the UK is going to get colder with increased climate change in the far future because you get weakening of these systems such as the AMOC, which is the Atlantic Meridional Overturning Circulation, which is responsible for the ocean basically transporting heat from the equator further north, which there's evidence that this may weaken with further climate change, so in the future we may see lower temperatures. But that is still highly uncertain and it's not going to happen for quite a while yet. What about the temperatures of the oceans surrounding the UK? So the UK near coastal waters have warmed steadily from the 1980s onwards at a slightly lower rate than that warming over UK land. So the most recent decade has been 0.3 Celsius warmer than the 1991 to 2020 average, and 0.9 Celsius warmer than the 1961 to 1990 average. So that's noticeably lower. So when we're comparing, say, to the land, we saw that it was for the last recent decade was about 1.24 degrees Celsius above 1961 to 1990 levels. And 5 of the 10 warmest years for UK near coast sea surface temperatures have occurred in the past decade. And this generally follows the global pattern in which land is warming faster than the sea. But why would land be warming faster than the sea? Well, firstly, water has a relatively higher heat capacity than rock or soil, or just the stuff that land is made of. And what does that mean? Well, heat capacity is really just a measure of the amount of energy a material can absorb before increasing by a given temperature, say 1 Celsius. So water, with its high heat capacity, can absorb a lot of energy before it changes temperature. So for the same forcing or the same amount of energy per unit surface area, the land will warm more. Second, potentially obviously, the ocean moves. Land doesn't move. So let's say the surface of the ocean has been heated. Vertical mixing in the ocean will dilute this warm water layer throughout the whole ocean body. Whereas in land, heat only really conducts downward, so it's much less efficient to kind of transfer that heat that the land has absorbed down further into the earth. You also get evaporation over the oceans, which absorbs heat energy and provides a cooling effect to the surface. So to recap briefly, the UK has seen a steady increase in average temperature both over the land and the sea, with the land warming faster than the sea. The UK land was 1.24 degrees Celsius warmer in 2015 to 2024 decade compared to 1961 to 1990 average, whereas the near coast UK surface temperature was 0.9 Celsius warmer in that same reference period. As well as increases in average temperature, we have seen increases in the frequency and intensity of extreme heat. So for instance, we're seeing more days over, say, 30 degrees in a given location. So that was temperature, but what about rainfall? So while the UK is traditionally known for its relatively wet climate, it seems that the rainfall patterns are also changing. So overall, since the 1980s, the UK has become steadily wetter, with these increases largely driven by changes in seasonal precipitation. So when we look at the most recent decade, 2015 to 2024, that was around 2% wetter than 1991 to 2020 average, and 10% wetter than 1961 to 1990 average. But if we now just look at the winter half year, which is between October and March, the rainfall in the most recent decade has been 6% higher than 1991 to 2020 and 16% higher than 1961 to 1990. So this suggests that although annual UK rainfall is increasing, this change is largely due to wetter winters compensating for less summer rainfall, meaning winters are becoming wetter while summers are actually becoming drier. Similar amounts of rainfall, if not increasing overall, but much more concentration of rainfall in the winter and much less rainfall in the summer. Now, long-term records seem to support this shift. In the 250-year England-Wales rainfall series, 6 of the 10 wettest winter half years have occurred in the 21st century. Some also other notable examples is that between October 2022 to March 2024, this was observed to be the wettest 18-month period on record for England, with South England receiving around 1.5 times the average rainfall. And rainfall variability is also increased, with some winter months much wetter than the average and some summer months much drier. So if we look at early 2026, it's already been notably wet, with, say, Camborne, that I was saying earlier, recording 242 millimetres of rainfall in January alone. So why are UK winters becoming wetter and summers drier? So as the UK winters become warmer, the amount of evaporation increases, as a warmer sea has more molecules of water with enough kinetic energy to become vapour, and a warmer atmosphere can hold more water vapour. And so we see more water vapour in the air, and a lot of this water vapour will then condense onto aerosols, which form cloud droplets, which then rain out as rain. And importantly, in the winter, atmospheric circulation brings a plentiful supply of moist, vapour-filled Atlantic air over the UK land, which is able to rise up and condense to form clouds, which then rain out on top of you. But in the summer, you may expect, using this same logic, that we'd see more rain as well, right? Because it's even warmer in the summer, so more evaporation, the atmosphere can hold more moisture, and we get more rain. But that is true. So we see a warmer ocean. We see we do see more water vapor in the air. But the key is here that rain requires cloud formation, which in particular requires rising of moist air particles. So as they rise, they become cooler, which allows them to cool down and condense onto these cloud droplets to form clouds. So the key really is we need vertical velocity of air. But in the summer, the UK often sees higher pressure regions over it, and so higher pressure means descending air parcels, which means negative vertical velocities, and so you don't get the vertical velocities required to form cloud droplets, and so the summers are drier. So what about sun? The UK is often thought of as a very gloomy place to be, a place where there's always clouds, constant fog, whatever. And indeed, it is pretty cloudy. But there is significant variation across the country, with places like the southeast being the sunniest, and other parts, such as Cornwall and parts of West Scotland, being significantly less sunny. But this may surprise you to hear that the UK's climate has become sunnier since the 1980s, driven mostly by increases in winter and spring sunshine. So the 2015 to 2024 decade has been 3% sunnier than 1991 to 2020 and 8% sunnier than 1961 to 1990 average. And surprise to many people, I would have thought, 2025 was in fact the sunniest year on record. So why is this occurring? One of the reasons we actually touched on earlier is that decline in sulfate aerosols. So as we said before, the sulfate aerosols scatter light and also increase cloud brightness. So more aerosols, more condensation onto these aerosols to produce cloud droplets, more clouds or brighter clouds reflect more light, and so less sun. So basically, the decline in pollution from burning less coal has caused this decline in pollution, which has made it sunnier. What about wind? Now, just as with sunshine, wind is not something we typically think about when we are talking about climate change. But observations do not suggest that the UK is becoming windier. In fact, the UK annual mean wind speed from 1969 to 2024 actually shows a downward trend consistent with the global average. As well as this, there are fewer occurrences of high wind speeds in the past 2 decades compared to 1980s and 1990s. So what would cause this downtrend? So there exists differential heating between the equator and the poles. Basically what this means is the equator is hotter than the poles, and this temperature gradient actually drives a pressure gradient. So in the tropics, the troposphere, which is the lowest part of the atmosphere where all the weather happens, is higher than at the poles, so higher altitude. And the altitude at which the pressure is the same in the tropics is higher than that at the poles. So say we're looking at the altitude in the atmosphere where the pressure is, say, 1,000 units of pressure, whatever, arbitrary units of pressure. That will be found higher up or at a higher altitude in the tropics than in the poles. And this means at a given altitude, the pressure at the equator is higher than that at the poles. And so we have a horizontal pressure gradient, which in balance with the Coriolis force, which is that rotational kind of force that we get from the spinning of the Earth or rotation of the Earth, causes a west to east zonal wind in the mid-latitudes, basically across the UK, with a velocity that increases with height, which is called the jet stream, basically. So a reduction in that gradient tends to reduce vertical wind shear and may weaken those mid-latitude jets. However, and this is a big however, it is not very clear how the surface wind will be affected by this. So we don't know necessarily whether the weakening of the mid-latitude jets will cause changes in surface winds. What about sea level? Well, sea level rise in the UK is accelerating. Since 1901, the sea level around the UK has risen by about 19.5 centimetres, with about 2/3 of this rise occurring in the past 30 years. And the last 3 years were the highest on record for UK annual mean sea level since 1901. But why is this? There are 2 main reasons for sea level rise. As the ocean warms, it expands. So about 40% of sea level rise was a result of thermal expansion. And simply as well, the second reason is as ice melts on land and flows into oceans, it increases the volume of the ocean. So about 45% of sea level rise so far has been attributed to this. So that covers the past to present of what we've seen in terms of how the UK climate is changing. In this section, we are now going to look a little bit about what we can expect in the future for the UK in terms of its climate. In this section, we'll probably find that a lot of this is just more of what we've already seen, but crucially, the changes we will see are likely to occur at a higher rate. But fundamentally, the long-term outlook will be determined by how much greenhouse gases we emit in the coming years, and high emission scenarios are far scarier than low emission ones. Before we talk about what the future may look like, let's talk about how we can get these estimates. And this brings us to the fascinatingly complex topic of climate modelling. First things first, the climate system is pretty complex because each part or each system within the climate system is interdependent, so it depends on the other parts. And this is something known as feedbacks. So for instance, if I wanted to look at how the temperature changes, we may see that an increase in temperature causes, say, an increase in evaporation and an increase in cloud formation. The clouds then reflect shortwave radiation or light back out into space and reduce the temperature, kind of acting as a negative feedback to restore the baseline. So Basically, it's critical that the major processes in climate models are well represented, otherwise that could throw off results. But how do climate models work? So climate models numerically solve the fundamental equations or physics equations that govern the Earth's weather and climate system. So climate models are built on physical laws that describe atmospheric motion and energy exchange, and these are solved on a 3D grid covering the globe. So I'm going to quickly take you through some of the physics-based equations that what you would find in a climate model. So the first one is the Navier-Stokes equations. It's also known as conservation of momentum. This equation basically describes how fluid moves in response to forces on it. So, for instance, pressure gradients that drive flow, gravity, Coriolis force, so force of the Earth's rotation, or internal frictions, viscosity basically, and they will really determine, say, the wind speed or the speed of a parcel of air, and the direction in which that's flowing. Those equations can be applied to the ocean as well, so for the flow of the ocean. We also have equations that represent the conservation of total energy within an air parcel or grid cell. So it really includes energy transported by advection or by the movement of the fluid parcel, a conduction, latent heat released during phase change, such as when water condenses, it's going to release heat. And importantly as well, takes into account radiation entering as a source or leaving as a sink. As well as this, we have the mass continuity equation. All this ensures is mass is neither created or destroyed unless something is added. For instance, have moisture and cloud microphysics equation, so deals with water vapor transport, condensation, evaporation, cloud droplet formation, precipitation. Radiative transfer equations describes how radiation moves through the atmosphere depending on wavelength. So shortwave solar radiation passes through the atmosphere, absorbed by the surface, whereas long wave infrared radiation is emitted by the Earth and absorbed and re-emitted by greenhouse gases. These processes then control the atmospheric heating and cooling, which then feeds into the energy conservation equations as sources and sinks. Equations of state. These relate thermodynamic variables such as pressure, temperature and density to each other. As well as this, we also have transport equations that kind of describe how substances move. For instance, water vapor and aerosols, what is the concentration of these in space with time, depending on sources of aerosols and sinks of aerosols, or whatever variable you're transporting. So effectively, what I'm trying to describe here is there are many processes that we have to consider and correctly represent in our climate model if we want relatively accurate results. And in terms of solving these equations, they are typically solved using numerical methods, also mostly finite volume methods. And the way finite volume methods work is we basically take the globe and we divide it into grid cells. So non-overlapping boxes, 3D boxes, and each cell will have one value for each variable, such as, say, the velocity or pressure or density. And the idea of doing this is kind of to ensure conservation. So whatever leaves your cell has to enter another one, basically. So the net change is related to kind of what's entering it, known as, say, the flux inward, minus what's exiting the cell, so the flux outward, plus kind of any sources within your cell minus any sinks. So if we're talking about, say, mass conservation, if there are no sources or sinks, the mass leaving one cell must enter an adjacent cell, and this guarantees mass conservation. So how do we solve these equations? Well, when using finite volume method approaches, we've already divided our domain, which is the Earth, into boxes called cells. And the cells are relatively large, say with horizontal length scales of around 50 kilometers, although this does vary. And like we were saying earlier, we have one value per variable per cell. And variables in this case are just things that kind of represent the state of the system. So, for instance, velocities of wind, pressure, densities, temperatures, concentrations of things such as greenhouse gases or aerosols, or chemicals in the atmosphere, humidity, and these values of each of these variables determine the state of the climate in that cell at that time. So if we have more boxes or more cells, we will have a higher resolution. So this is more values in space. So one value per variable for each grid cell doesn't seem that much if it's 50 kilometers. 50 kilometers is quite a big area. So more boxes means a higher resolution. But that does have a major trade-off of being quite a lot more expensive. So more cells means more calculations that have to be solved in the model. We can then step forward in time using the variables from the last time step, so the current state, to calculate the new state using our equations from earlier that show how does the state evolve with time and space. That's what those equations really represent. And we also have to deal with time resolution. So if the model has very small time steps, then that's also more expensive. So it's really about trade-off of finding like what's a good time step to use, or what's a good length scale to use that's not too expensive but also yields us good results. And because much of these processes occur on scales much smaller than the grid sizes, there's often additional modelling to represent kind of the internal workings within each cell, so subgrid scale processes. And these models are often very expensive to run in terms of compute resource. So basically you've just got many equations solved for each cell, and there are many cells, and you're also doing it for each time step, so just a huge number of equations. And so weather forecasting or climate modelling services have typically a lot of supercompute power. So for instance, the UK Met Office has a computer or 3 large computers with around 460,000 CPU cores, and it's currently the fastest machine in the world for weather and climate modelling. So yeah, serious computing resource required to do this modelling. And with models, there's always going to be uncertainty. No model is perfect. It's just a general prediction based on physics. So what are the sources of uncertainty in climate models? So one source is actually just natural or internal variability. So even with identical forcing, for instance, the same greenhouse gas concentrations in the atmosphere, small differences in initial conditions, well, the starting state will produce different future states. And because we cannot know the initial conditions to perfect accuracy, there's no way we can perfectly predict the future, even if we did have perfect models. So to get around this, we typically run multiple simulations with slightly different initial conditions, initial states, to estimate the variability in the end states. As well as this, there's just general uncertainty. This isn't really to do with modelling, but it's just to do with uncertainty related to, say, future emissions of greenhouse gases, because that's very much depends on what humans do in the future. So we don't really know exactly what the future greenhouse gas concentrations will look like, as well as concentrations of different aerosols in the atmosphere. As well as this, there is uncertainty in kind of the model structure, like how the model is set up. So differences in parameterizations related to how clouds are represented or convections represented, and the representation of small-scale processes. The way these different processes are represented can have a relatively large impact. For instance, how much does changing the carbon dioxide concentration in the atmosphere affect warming? I.e., what is the sensitivity of the climate to greenhouse gas concentration? And you may have thought that this will have been kind of worked out a long time ago, but it's actually hard because of these feedbacks. So, say, increasing the temperature can increase the clouds and reflect radiation out to space. Or in the other direction, you could have the higher temperatures melt sea ice, which then absorbs more short-wave radiation, which causes more warming. That's the opposite, it's a positive feedback. So these feedbacks do increase the uncertainty of such things. Other ones are like, how much will the carbon cycle change? E.g., will the ocean and land absorb more or less carbon in the future, and by how much? And obviously the models are compared to real observations. So for instance, you could run a model from the past to the present using the conditions of the past to see, like, does the model predict the present conditions? Obviously we cannot check exactly what the future conditions are going to be because we haven't experienced them. So that was a pretty brief overview of climate modelling, and I'm sure I oversimplified many areas there. But let's get on to the future bit. So what may the UK climate look like in the future? So by 2050, UK winters are projected to be around 1.2 Celsius warmer and 5% wetter than the 1981 to 2000 average. We're also expecting a greater rainfall intensity with more wet days. But individual winters may vary quite a lot, with occasional cold and dry winters still possible, but just less likely. We'll also see more hotter and drier summers, so by 2050 summers are projected to be around 1.6 Celsius warmer and 13% drier than the 1981 to 2000 average, with the strongest warming in southeast England. So hot summers, such as those found in 2022, will become much more typical by 2050, and lower overall rainfall will reduce in a higher drought risk, but potentially more intense downpours when rain does occur. Sea level will continue to rise for centuries even if global temperatures stabilise, and by 2050 the UK sea levels are projected to be around 10 to 30 centimetres higher than the 1991 to 2000 average, 1981 to 2000 average, with highest rates of sea level rise expected along southern UK coasts. It's important to reiterate here that the magnitude of these effects that we have just talked about will really depend on future emission scenarios. Okay, so that was about everything I wanted to talk about in this episode of the Curiosity Monkey podcast. I appreciate that it's kind of a long episode packed full of different statistics, and I did talk a bit longer than I was expecting on climate modelling as well, but that's just because it is quite an interesting topic in my opinion. But what can we summarise from this? Well, really, if I wanted to make any point at the end of this episode, it's that the climate is changing sufficiently fast, such as the climate in 2015 is different from that of 2025. So only in one decade have we seen changes. So it's going to be very interesting to see how this next decade unfolds. So that is everything for this episode of the Curiosity Monkey podcast. I hope you enjoyed this episode. I will put all the links to the papers and data used for this episode. If you have any episode suggestions, please don't hesitate to contact at thecuriositymonkey1@gmail.com, or we have Instagram as well at thecuriositymonkey. So yeah, thank you for listening, and we'll see you in the next episode. Goodbye.